This is the music of the planets, not someone's fantasy. This is an animation of a real-life system of 178, in which 6 planets are known. The movement of 5 of them is surprisingly synchronized in the orbital resonance. The rhythm of the sounds that the planets make here is not accidental. The planet makes a sound either when it makes a full circle in orbit or half a circle, or when 2 or more planets line up. Yes, the notes were chosen specifically for clarity and effect. But even if the planets were to emit the same note, the repetitive, ordered rhythmic pattern would not go away. Planets sing only in animation. However, their synchronous orbital dance takes place in reality. And this can be demonstrated not only with the help of sounds, but also with visual techniques. Here are the orbits of our native Earth and Venus. And if you draw a line through the points of their maximum convergence, then the planets draw a pentagram. What would that mean? Well, if, as both planets move in orbit, a line drawn from planet to planet is constantly applied, then in general, in the end, it turns out to be such a bizarre pattern. What does it all mean? And is there any hidden meaning in this? Well, hidden is not hidden, but there is some kind. People have been searching for order and regularities in the universe for centuries and even millennia. And they don't always come to the right conclusions in these searches. It's easy to imagine how someone, after seeing what I just showed you, will decide that everything is too orderly here. Obviously, it couldn't have happened all by itself. Perhaps the planets were arranged by someone in such configurations. But whatever the real reason, it all looks really interesting. And it would be nice to try to figure out how it turns out. Today, we will talk about orbital resonances, what types they are, how often they occur in the universe. We will analyze some interesting examples, and most importantly, we will try to understand how planets synchronize in such an amazing way that creates orbital resonances, and what they, in turn, lead to themselves. Well, I'm Andriy, and you're on the Cosmos channel simply.
You won't guess where he'll find us.
It is interesting that people were engaged in the peculiar music of the planets 2,500 years ago. Well, like people. One particular person, Pythagoras. Well, that's according to the stories. We don't have a lot of reliable information here. If you believe the legends, he was the first to find out that musical notes can be described mathematically. But he did not stop at strings of different lengths and properties, but transferred similar principles into space. The logic here is as follows. On Earth, objects in motion make sounds. The planets are also in constant motion, as it was then believed, around the stationary Earth in the center. Since they move, it means that each planet can produce its own unique sound, its own note, which people, however, are not able to hear. This idea of planetary music is called the harmony of the spheres. The famous astronomer Johannes Kepler, the author of Kepler's laws, which formed the basis of Newton's law of universal gravitation, argued about something similar much later. In his work Harmony of the World, he also tried to find a connection between the movements of the planets and musical harmonies. And there are already some similarities with the idea of orbital resonance. With the advent of the law of universal gravitation, the question of the stability of planetary systems became more acute, and one of the first orbital resonances was discovered by Laplace. This is the resonance of the 3 Galilean moons of Jupiter, Io, Europa, and Ganymede. Now, of course, we have a completely different understanding of all this. We know a large number of examples of resonances in space of specially synchronized systems. At the same time, we also see that this is not happening everywhere. In general, The resonance, according to the explanatory dictionary, is, I quote, the phenomenon of amplification of sound, electrical, mechanical vibrations occurring in any oscillatory system, under the influence of external influence, provided that the purity of the vibrations of the external force coincides with the purity of the natural vibrations of the system. In general, there is a lot of connection with sound, so the associations that we talked about before are not surprising. Most likely, most of those who know something about orbital resonances, when they hear this phrase, think exactly about those resonances that I showed at the beginning. But in fact, there are several types of them, and there are three main ones. The most famous resonance in English is called what can be translated roughly as the resonance of the average motion. But according to my feelings, it is mostly just called orbital resonance everywhere. Although the nature and cause of the phenomenon is quite tricky, and we will talk about it later today, the essence of the visible effect is quite simple. The definition here usually sounds something like this. Orbital resonance is a phenomenon in which the orbital periods of two or more bodies orbiting a larger body are correlated as small natural numbers. Denote resonance and so. 22132 to 42221, one of the simplest examples is a 2-to-1 resonance. This is when two bodies moving in orbits around a third body, for example, two planets around a star, or two satellites around a planet, located from the central body at such distances that it takes exactly twice as long for the far body to make one orbit than to the near body. And now let's build such a system ourselves in the Saint Box universe. Let's take the Sun, place the Earth at the distance at which it is actually located, on average from the Sun, that is, by 1 astronomical unit. For greater accuracy, we will manually adjust the orbital period or year so that it lasts 365 days. And now let's put another Earth and give it the duration of the orbital period, exactly twice as long, 730 days. For clarity, we will increase the size of the planets so that they can be seen and run the model. Apart from the obvious that it takes exactly twice as long for a distant planet to make a circle in orbit than a near one, we kind of asked it ourselves. It is also interesting that planets always meet at the same points of their orbits. And this is an important point, which we will talk about in more detail today. Here I made another example of a 4-2-3 resonance. The conditional loop starts at one point. During the cycle, the outer planet manages to make 3 circles to the inner 4, and at the end, they return to the same point from where the cycle began. In a 5-to-1 resonance, the planets meet several times during the cycle, but eventually return to their starting point. It is not surprising that it seems that the system with resonance seems to have been created on purpose. We had to adjust the duration of the orbital periods in the model so that the planets always meet at one point. But to avoid resonance, you can just sculpt planets at random, almost anywhere. Although in fact everything is trickier there. In the system that I showed at the beginning, then 178 is a whole chain of resonances. Of the 6 planets, 5 are in resonance, to 2, 4, 2, 6, to 9, to 12. That is, at the same time, while one planet makes 2 orbits, the next 4, then after it 6, and so on. Only we started from the end here. But before we talk about how, in general, it turns out that the planets synchronize their movement, let's see what other types of resonances there are. Many of you are familiar with another type of resonance, and we have talked about it many times. They just didn't use the word resonance. It is called spin-orbital resonance, and in principle, based on the name, you can understand what the point is. Spin is the rotation around the axis, orbital is the motion along the orbit. Well, actually here, we are talking about the synchronization of these 2 types of movement. We talked about this in the context of tidal capture or synchronous rotation. And the closest example is, of course, our own moon, which makes 1 revolution around the axis in the same time, as it does not circle around the orbit. Because of this, we always observe only one side of the moon from Earth. It turns out that the moon is in a 1-to-1 spin-orbital resonance. What is common here with the orbital resonances, which I have talked about before, is that there is a mechanism, as a result of which the object is not in such a resonance at first, and then, due to tidal interactions, it turns out to be locked in this resonance 1-to-1. And this is the logical outcome of orbital evolution for many bodies. Actually, almost all of the major satellites of planets in the solar system are in a one-to-one spinal orbital resonance, or in other words, in tidal capture, as do some planets that are close to their stars. Well, as in the case of other orbital resonances, they can be different. Not just one-to-one. In the solar system, Mercury is a good example. It rotates slowly around its axis, but is not in tidal capture. It has a 3-to-2 spinal orbital resonance. It makes a circle in orbit around the Sun in about 88 days, and the planet rotates around the axis in about 59 days, which is exactly what we are given the ratio of 3-to-2. Another type of resonance is called secular. It's not what you think it is. In English, it is called a skill, and one of the translations of this word is long-term. And they are called so not by chance. The cycles of these resonances take place on much larger time scales, thousands and even millions of years. And here, not the bodies themselves are involved, but their orbits and orbital parameters, and their precession. As we know, there are no perfectly round orbits, and they are all elongated to one degree or another. Let's take for clarity an orbit with a high degree of ellipticity. Such an orbit has a point closest to the central body, in front of the center, and the farthest in the center. Also, between the front of the center and a line can be drawn along the center, which is called the apse line. So the orbit and this line are not always directed in the same direction. Not only does the body move in orbit, but the orbit itself is constantly shifting in this way, which is called a recession. And this precession of the orbits of two or more bodies can also be synchronized in a certain way. If we take a simple version, when there is no resonance, then the center of the orbits of the two bodies is directed in different directions, and when there is resonance, precession occurs synchronously. I've only found one animation that would show this. I'll leave the link in the description. Such synchronization may affect other parameters, such as the inclination of the orbit and others. But let's go back to the more familiar orbital resonances. This is synchronization, that is, the transformation of data into sound of another system, with a long chain of resonances, the longest known to date. If in that 178, 5 of the 6 planets were in resonance, then here are all 7 known planets. The more such a chain is, the less likely it seems that it could just be a coincidence. Spin-orbital resonance one-to-one, or tidal capture, by the way, also often confuse people. They say, how did it so happen that the rotation time around the axis is equal to the time of the circle in orbit? Clearly something is not clean here. But just as there are mechanisms explaining this, in quotation marks of coincidence, so there are mechanisms in the case of ordinary orbital resonances. First of all, you can try to look at this question naively. So, in a system with resonance, we have orbital periods that coincide in a certain way. Let's say one planet has 100 days, and the second one has 200. What does this duration depend on? Why 100 days, and not 110? Well, everything is quite simple here, and everything rests on the distance to the central body. Just as we need to accelerate a rocket to a certain speed, so that it does not fall to the ground, but goes into orbit around the Earth. And the device remains there. In order for the planets not to fall into the Sun, they also need a certain orbital velocity. Moreover, the closer to the star, the stronger its attraction, and the higher the orbital velocity should be. And the speed does not depend on the mass of the smaller body, but on the distance. You can conduct a small experiment in the universe box. Yes, this is far from the most accurate tool, but it demonstrates the basic principles of classical mechanics quite well. Let's take the Earth. Again, we place it at a distance of 1 astronomical unit, that is, at the real average distance from the Sun. And just by placing the planet at such a distance, we see that the orbital period is equal to 1 year. And the orbital speed is equal to 29.7 of kilometers per second. Everything is as it really is. And now, we will remove the Earth and put a pigeon in its place. No, let's better watermelon at the same distance from the Sun. And what do we see? The same orbital velocity and the same orbital period. There may be a small error. To place it at one point with an accuracy of up to a millimeter is a little difficult here. Well, a watermelon in the same way, having the right speed for this distance, calmly flies itself in orbit around the Sun. and does not fall on it. That is, again, I remind you that we are still looking at the question naively. One might think that in order for the planets to be in a 2-to-1 resonance, they just have to form at the right distance. Let's say one is on such that its orbital period is 100 days, and for the second one 200 days. And considering that there are hundreds of billions of stars in our galaxy alone, and hence planetary systems, probably from time to time there will be such systems in which planets have formed at such a distance that their orbital periods are in resonance. However, in this case, the phenomenon of orbital resonance would be rare. But if we look at how widespread this phenomenon is in the galaxy, we will see that it is quite rare in Notaka. Resonances are observed in about 5% of open planetary systems. And resonances involving more than 2 planets are even rarer. Well, that is our answer, it's just a coincidence. In the big universe, even very rare events happen from time to time, and that's it. But it wasn't there. In general, the idea that in some cases resonances in the system are present of the formation itself, or almost of the formation itself, is being considered by scientists. But still clearly it can't work in all cases. You yourself may well have noticed a hole in this logic, given what we already know about the evolution of planetary systems. And what we know is that planets generally do not form at the same distance from the star and stay there forever, but they tend to migrate. Especially in the early stages of the existence of systems, when they are much more chaotic. Planetary systems are dynamic and complex. There are many bodies of different masses in them. Not only does a star affect planets and small bodies with its gravity, but all bodies affect each other. That is, on the one hand, yes, planets in theory can form, at such a distance from the star, to be in resonance. But then they need to stay at this distance. But also, since the planets are moving, they can settle at such distances after throwing around the system to get into resonance, which is also possible. And there are mechanisms that help this. Often, when they give a brief explanation of the essence of this phenomenon, they say something like the following. And first of all, that gravity is to blame for everything. They say that planets, periodically meeting, give each other a gravitational push, and thus one slows down the other or accelerates. Usually he gives an analogy with a swing. When one person swings on a swing, and the second pushes him. Depending on how to push, you can get different results. If you push out of sync, or at random moments, a person on a swing will flounder at random. But if you do it synchronously at strictly defined moments, you can increase the amplitude of the swing. And planets in resonance can do about the same thing. And depending on the situation, this can lead to different outcomes. The system can become more stable and remain in resonance. There are mechanisms of self-correction when the planet, coming out of resonance, returns to it back. Or vice versa, it can lead to destabilization when the body comes out of resonance and does not return to it. This is especially true of the situation in which we have one body much more massive than the second. For example, a planet and an asteroid in resonance. But all this again does not explain how bodies can be in resonance if they have not been in it before, or how they can stay in resonance if they hit it. In other words, if, say, 2 planets were initially lucky to form at such distances that they are in a beautiful resonance, and if we follow the logic that with constant encounters the planets push each other gravitationally, it turns out that sooner or later, they should disperse from each other and come out of resonance. And we are not yet considering other mechanisms due to which planets can move through the system. This is also happening. And not all resonances are not that eternal, but even stable in the long term. We know that satellites and planets move through their systems. Yes, if there were some perfectly symmetrical system of 2 bodies, where the orbit would be perfectly round, the bodies themselves perfectly symmetrical, there would be no other bodies, and so on. Then such a planet in theory could remain at the same distance from the star always. But in practice, of course, this is not the case. Both planets and satellites move through their systems, not only shortly after formation, interacting with matter in the protoplanetary disk that has not yet dispersed and other bodies, but also billions of years later. The most famous example is our moon, which, due to tidal interactions between the Earth and the moon, moves away from the Earth by about 4 centimeters per year, like many other satellites in the solar system. If the satellite is too close, then, on the contrary, it may eventually fall on the planet, as, for example, the satellite of Mars Phobos, which is gradually approaching the red planet. Well, in the early stages of systems, planets migrate constantly. It is believed that hot Jupiters most likely initially formed farther from their stars, and then got closer. Well, there were more bodies in our system at its dawn. They affected each other gravitationally, swapped places, and so on. He flew an entire planet the size of a butterfly to the young Earth, which led to the formation of the Moon. There are actually a lot of nuances here. For example, the Earth is still slightly moving away from the Sun by a few centimeters a year. And why? But because the Sun is getting lighter. As a result of thermonuclear reactions, the Sun generates energy and loses it through radiation. And the energy and mass are equivalent. In addition, the Sun loses mass through the solar wind. The smaller the mass of the Sun, the weaker its gravitational attraction and influence on the Earth. Here it is very slowly and moving away. In short, planets, like satellites and other bodies, do not sit still. Not only do they move in orbits, but the orbits themselves change over time. So it is easy to imagine a situation in which, say, two planets moving through their system one day find themselves in such orbits or at such a distance from their star to get into resonance. But here we have the same question as with a successful formation. If they were moving anyway, they probably will continue to move on. Why should they stay in these orbits? And, by the way, our solar system can be a good example of possibly destroyed resonances. Yes, we have many examples of resonances. The already mentioned resonance of Jupiter's moons. Another striking example is the resonance of Neptune and Pluto, 3-2. This, by the way, is a useful resonance. The orbits of Pluto and Neptune intersect, which means that in theory they could collide. But because they are in resonance, they never meet. And then little Pluto was first downgraded to a dwarf planet, and then he would also have gone to Neptune, and for the time being. But for some reason, there are no resonances among the main planets of the solar system themselves. At least, they are not particularly heard in examples when it comes to resonances. In fact, some planets, if not in resonance, are very close to it. Strictly speaking, what we call resonance is naturally not synchronized to the nearest second. But in the case of the solar system, we have a bigger scatter. Jupiter and Saturn are almost in resonance 5-2. And this can be checked. Jupiter has an orbital period of 4,332 days, and Saturn has 10,759. 4,332 times 5, and we get 21,660, and 10,759 times 2, and we get 21,518, which in general is very close, but still there is a slight difference of 142 days. I showed an animation of Venus and Earth at the beginning, and they are also close to the resonance of 13-8. Earth and Mars are close to a 2-1 resonance, although there is a bigger difference there. Just here the situation may be such that earlier the resonance of, say, Jupiter and Saturn was even closer, but over time, it became out of sync. But in other planetary systems, we still observe more precise resonances. And then either we were just lucky to see them at the moment before they collapsed, which in principle is also true in its own way, because they are somehow not eternal. But still, they can remain stable for a long time, 4 billions of years. Which means that something must lock them in this position for some time. This is the peculiarity of resonant orbits. This is the asteroid belt of our solar system, located between the orbits of Mars and Jupiter. This is not a narrow strip. It is about 1 astronomical unit wide, that is, more than 150 million kilometers. That is, some asteroids in it are closer to the Sun, while others are much further away, and they have different orbital periods. They are not distributed very evenly. But, as usual, such illustrations can't show all the nuances, so it's not very noticeable. If we plot a graph where we have the distance to the Sun on one axis and the number of asteroids on the other, then we will get this. And we see that here at a distance of 2.5 astronomical units from the Sun, or there are almost no asteroids here. These gaps are called Kirkwood slits. But why is it empty, or almost empty at these distances? And so far in this picture, I have not shown you one important detail. Here it is. These gaps are not located randomly. They are located at a distance from the Sun, at which asteroids fall into resonance with Jupiter. Here we see resonances of 3 to 1, 5 to 2, 7 to 3, and 2 to 1. Asteroids that used to be there received regular gravitational shocks from Jupiter. Jupiter is incomparably more massive than asteroids, and as a result, these tremors force them to leave these areas. Thus, over time, they are cleared of objects. And we see these very cracks. This is a very clear example of the effects that cause orbital resonances in the case when one body is much more massive than the other. But you might have a question. And what exactly does it matter if there is a resonance in this case or not? If we have two bodies moving in orbits around the third, they will in any case periodically meet at the nearest points. In any case, at these closest points, the gravitational influence of Jupiter on the asteroid will be maximum. What difference does it make if it always happens in the same place, or always in different places? And here the important point is that the orbits are again not perfectly round, but elongated. Interestingly, there are very few detailed, and at the same time accessible explanations of how it works on the internet. I found one article and a couple of explanations based on it. Another article and a cool video from Steve Mould. Of course, I will leave the links in the description. So, if we have circular orbits, and two bodies meet at some nearby points, it does not matter at all where exactly this happens. Here we drank here. The distance and effects should be the same in theory, but in life, of course, this does not happen. The article considers a special case for clarity. The orbit of a body that is closer to the central object has a small eccentricity, and is quite close to circular. But a more distant body is in a noticeably more elongated orbit. Also, for convenience, the inner body is much more massive than the outer one, so that we can neglect the gravitational influence of the far on the near and, conversely, focus on how the near affects the far. If we assume that the bodies are in a simple 2-to-1 resonance, then they will always meet at the same point. The situation in which the place of their meeting coincides with the obsidian line passing from the lane in the center, and they meet from side in the center will be stable. Why? Let's figure it out. These pictures from the articles show a slightly different situation. The meeting place does not coincide with the apse line. Here it is shown by long dotted lines. And here we see two situations at once. Two planets shortly before the meeting, at the points of maximum convergence, and the planets after this meeting. And there are also some arrows here. The arrows show the direction of the individual components of attraction. And the length of the arrows is also not random. If the point of maximum approach does not coincide with the obsidian line, then how does the larger planet affect the smaller one? Before the rendezvous, when a more massive planet lags a little behind the distant one, it not only attracts it in the direction of the inner orbit, but also pulls the distant planet back. And after the rendezvous, on the contrary, it pulls the planet behind it. If the meeting had taken place exactly on the obsidian line, these two effects pulling back against the direction of movement along the orbit, and, conversely, pulling forward in the direction, would have been equal, since the halves of the orbits would have been symmetrical. Here I have dark blue arrows of the same length indicating this. But in this case, when the meeting is elsewhere, it's not. This means that here, before the meeting, the inner planet pulls the outer one a little stronger than after the meeting. For clarity, the dark arrow on top is longer here. In fact, the inner planet is gradually slowing down the outer one. We have already talked with you today about the fact that in order to stay in a certain orbit and not fall on the central body, you need to maintain a certain speed. Even a very rarefied atmosphere at the altitude of the IS orbit is enough to slow down the station slowly and correctly, which is why, without periodic engine starts, the station would eventually fall to Earth. The outer planet has no such luxury as engines. Therefore, due to this deceleration, its orbit is gradually decreasing. And once the orbit changes, it means that the time it takes to make a circle around the orbit also changes. Which means that the points at which the planets meet gradually change. At some point they what? Coincide with the apse line. with a place where the component of attraction against motion and in the direction of motion will finally be balanced. And it will be a stable configuration. The planets will be locked in such a resonance. In a similar way, this will work if the planet pulls the second one after the meeting at the maximum approach, only in the opposite direction. In the real world, the planets, however, will not remain in this position forever anyway. After all, as we have already said today, there are other mechanisms that cause satellites and planets to migrate, tidal forces, as in the case of the Moon, or the loss of mass of the Sun, as in the case of the Earth. In addition, in reality, in addition to these three bodies, there are actually other planets that also wave their own right to left. Gravity? In short, even a stabilized system will still synchronize sooner or later. But it is interesting that in this case, the mechanism that I described above may start again. And the planets will return to the most stable configuration again. And it can go on for a long time. And if this mechanism is stronger than other influences, the system can be in resonance for a very long time. This is an example of a stable self-correcting resonance. And it perfectly shows what is so special about resonances, and not about random encounters of planets in random places. In this example, we saw how one more massive body, which is in resonance with another, actually changes its orbit. In a similar way, Jupiter cleared out sections of the asteroid belt and created the Kirkwood crevices. Of course, now we have described a very simplified case, and in general, in practice, resonances are more often unstable. The swinging swing overdoes it and launches the swinging one far away. The orbits have different eccentricities and inclinations and so on. And as a result, in 95% of cases, the resonances eventually collapse. But still, we sometimes come across amazing systems like TRAPPIST, one with as many as 7 planets in resonance. Here, by the way, scientists believe that perhaps the resonance was able to persist for so long. The system, by the way, is older than our solar system because for some reason, in the early stages of the planet in the system, experienced not so many collisions with other large bodies. If the period of the so-called late heavy bombardment, there was the same as in our system, then large collisions would beat the planets from their orbits and the resonance would collapse. But we are still observing it. In general, there is still a lot of interesting things here. For example, there may be retrograde resonances, when bodies in orbits move in opposite directions and not in one, as it happens in most cases. Another special case of one-to-one resonance. Here it turns out that since the orbital period of the two bodies is the same, then the planets or satellites are in the same orbit. Well, I talked about a similar situation, about whether it is possible, in a separate video about anti-Earth. So watch it if you haven't seen it yet. There are, of course, many more nuances here, but I hope now it is at least a little clearer how, in addition to a random coincidence in certain situations, slowly migrating planets that are not in resonance, once in it, eventually remain in it for a long time. I hope it makes it a little clearer what kind of pushing the planet is. The analogy with the swing has become a little deeper. No magic, fine-tuning and astro-engineering from super-advanced aliens. A pity. Friends, don't forget that everyone who supports me directly on Boost, on Patreon and on YouTube, gets an additional exclusive video every 2 weeks, as well as other nice bonuses depending on the level of support. Be sure to subscribe to my Telegram channel and contact group in order to receive additional space content almost every day. And always stay in touch. Thank them again. Bye.